Hello everyone. On this video we will be looking at the extreme value theorem and how we can use it to identify your absolute extrema or your absolute minimum and maximum. Okay, so what if we let f of x be defined on an interval, clean that up a little bit, from A to B. Okay, what does that tell us? Then we know that there's some f of a value c that is the minimum of that function f of x if that value at c is less than or equal to f of x for every x in the interval. Okay, so for every value c has to be less than that x value, for every x value in that interval. Okay, what else does it tell us? Well, it also tells us that f of c is the maximum of f of x if f of c is greater than or equal to f of x for every x in the interval. Alright, so what if we look at this on a graph? Okay, so what if we draw our x and y axis? So we have our x and we have our y, and let's say our graph kind of loops like this. Okay, well, of course this is your A and this is your B. Okay, or better yet, instead of A and B, I'll make that C number 1 and C number 2. Just kind of keep it with the definition. Okay, so we see here that our highest y value is our f of c number 2. So our maximum is f of c, let me clean that up a little bit, f of c2. Okay, now we can see here that this c value, and we'll just call that just regular ordinary c, that's our minimum because that's the lowest y value, is f of c. Alright, now let's draw another xy axis and we can take a look at another variation of maximum and minimums. Okay, so if we draw our xy axis here, so we have our x and we have our y, and let's say we have the very same graph that's up here, but instead you have an open-ended graph. So instead of a closed circle, you have an open circle on the ends. Okay. And we can see here that because of that open circle, there is no maximum. So there's no maximum value here. So if you know there's no maximum value just by looking at the circle, well, why is that? Because you can look at it and see, let's say this is right over x equals 2. Okay, so if this is over x equals 2, just to pick any value, and there's no maximum value at x equals 2, that means it can go to 1.9. It can go to 1.99. It can go to 1.999. It can go to 1.99999. It can go to 1. And you can just keep adding decimal points, and it'll keep getting a little bit bigger, a little bit bigger, and a little bit bigger, even though it will never actually equal 2. Okay, that's why there's no maximum value here. But because about this point, there does exist a minimum value. So the minimum value is at f, and we'll call that c for this graph. All right, so what if we draw one more? Let me move this up a little bit. So if we draw another xy axis. So we have our x and we have our y. And let's say if we draw another graph, pretty much looking like that one, where this is closed in, it goes down to an open circle, then goes back up to a closed circle. Alright, so you can see here at this C value that there is no minimum. Okay, because once again, you can just get closer and closer and closer and closer to that value and not actually equal that value. So there's no minimum here, but your maximum, we'll say this is over C number 1. Okay, so we know our maximum is f at C number 1. Okay, so there are different forms of having an absolute minimum but no absolute maximum, or an absolute maximum but no absolute minimum, or you can have neither one, or you can have both. So there are different variations. There's no rule saying that you can only have one or the other. You can have both, or you can have neither. Okay, so if this would have been an open circle here, there would have been no maximum and no minimum. Or in this case, you can have both, or you can have one or the other. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our example. All right, so let's say for example, before we get into our example, it would help if we had the actual definition of the extreme value theorem. Or EVT. Okay, so I gave you kind of an idea, but no exact definition. So if f of x is continuous on a closed interval from a to b and differentiable on an open interval from a to b, then f of x has an absolute maximum which really is just another way of saying your largest y value. So I'll put that underneath there. So it's like your largest y value and absolute minimum. Which is the smallest y value. All right. So let's look at a couple of examples. Okay, so let's say, for example, if we have f of x equals cotangent of x on the interval power over 4 to 3 pi over 4. Okay, so if we wanted to look at this and wonder if this has an absolute minimum or maximum, we'd have to look at what cotangent of x really is. So if you note this, that cotangent of x is actually equal to cosine of x over sine of x. Okay, so what does that tell us? Our denominator can't equal 0. So that means sine of x can't equal 0. Well, what does that tell us? That x can't equal 0, pi, 2 pi, and so forth and so on and so on. 3 pi, 4 pi, 5 pi, anything that would make that equal 0. Now, it's lucky for us because pi over 4 and 3 pi over 4 doesn't cross those points. So cotangent of x is continuous between pi over 4 and 3 pi over 4. Okay, because pi over 4 is bigger than 0 and less than 3 pi over 4 is less than pi. So it's between those two. Alright, so since all of these, since it's continuous and differentiable on that interval, we know that it's guaranteed and is guaranteed by the extreme value theorem to have an absolute minimum and absolute maximum. Okay, now we'd always plug these in and find what they are, but this just tells us that it exists. Okay, so with the extreme value theorem, it doesn't tell you what the absolute maximum and minimum are. It just tells you that if a certain set of circumstances are met, then we know it exists. Okay, so it won't necessarily, like I said, it won't tell you what it is. It's just meant to tell you that whether or not you should go through the trouble of looking for the absolute minimum and maximum. Okay? All right, so let's look at another example. Okay, so what if we have f of x equals 1 over natural log of 3x on the interval 1/4 to 2. X equals 1/4 to 2. Alright. So, what do we know? Once again, we know that our denominator can't equal 0. Okay. So, since natural log of 1 equals 0, we know that we cannot let that equal 0. So we know that x can't equal 1/3 because 3 times 1/3 is 1. Natural log of 1 is 0, so you'll have a denominator of 0. Alright, so since x can't equal 1/3, we can see that our interval will be broken up because 1/4 is actually on the left of 1/3 and 2 is on the right. So since 1/3 is between 1/4 and 2, that lets us know it's not continuous. Okay, so that graph is not continuous between 1/4 and 2 because you have that one point where x can't equal a value in between those. Okay, x can equal everything else, but it can't equal 1/3. Okay. This means the function 1 over natural log of 3x is not continuous. on the interval x equals 1/4 to 2. Okay, so this really lets us know that there's no guaranteed absolute maximum and absolute minimum by the extreme value theorem. Okay, so this one's kind of telling you, okay, by the extreme value theorem, we can't guarantee that if you start searching for an absolute minimum and maximum, there's no guarantee you'll find one. Okay, so basically they're telling you don't bother. All right, so hopefully this made sense, and I will see you on the next video.